Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 18, Organic Chemistry 1. In today's lecture, we will continue on chapter 5, the study of chemical reaction. In mechanism, we study the step-by-step sequence of elementary reactions by which overall chemical change occurs. At this stage, we classified organic reaction into two categories: free radical reactions, ionic reactions. In free radical reactions, a free radical can be defined as an atom or molecules containing one or more unpaired electrons in valence shell or outer orbit and is capable of independent existence. The odd electrons of free radical make it unstable, short-lived, and highly reactive. In radical reaction mechanism, we used single-headed arrow to depict the movement of single electron. Okay, for two electrons, we used this arrow double-headed. A chain reaction involving free radical can usually divide in three distinct processes. Number one, initiation. Number two, propagation. Number three, termination. In initiation reactions result in a net increase in a number of free radicals. The various ways by which free radical may be generated are thermal cleavage, like the one of the azo compound upon heat, okay, homolytic to form nitrogen gas and create R radical. Photochemical cleavage, like the one in halogens, chlorine, with light, homolytic cleavage to form 2Cl radical. Decomposition reaction, if you have benzoyl peroxide, you heat it up, form radical, followed by elimination of CO2 to form phenyl radical. Propagation reactions are those reactions involving free radical in which the total number of free radical remains the same, and termination from the name, okay, it is terminating the reaction, means that disappearance of free radical. So free radicals combine to form a more stable species like chlorine radical will react together to form chlorine molecule. Propose a mechanism for free radical chlorination of methane. So methane with chlorine in the presence of light, UV light, chloromethane and HCl products. Calculate delta H naught for each step. Calculate the overall delta H naught for this reaction. Given bond dissociation energy, HCl carbon Cl bond, carbon hydrogen in methane, carbon chlorine in chloromethane, and CCl bond. So initiation will be the chlorine homolytic cleavage upon shining with UV light, homolytic cleavage to give chlorine radical. We need here 242 kilojoule per mole. This is endothermic reaction, so we have to give this energy. That's why it is with plus sign. Propagation step. Here, carbon Cl homolytic fission, leaving radical on the carbon, methyl radical, and the formation of HCl. So we break carbon hydrogen and we form HCl bond. Breaking carbon hydrogen in methane equal to 435 kilojoule, and again it is endothermic reaction. And here we form HCl, and HCl4 means that gives out energy, that's minus 431 kilojoule. So for this step to occur, we need to give the system plus 4 kilojoule per mole. Only 4 kilojoule, all right? Okay. Now, from the first step, the methyl radical will react with chlorine molecule, okay, forming carbon Cl bond and cleave the CCl bond. For the CCl bond, we have to give 242 kilojoule per mole. For the formation of carbon Cl in chloromethane, we give out energy minus 351 kilojoule per mole, so the total is minus 109 kilojoule per mole. For the whole reaction, it will be plus 4 minus 109 will be minus 105, and the net reaction, the overall reaction, is exothermic reaction. The initiation step is not added to give the overall enthalpy change because it is not necessary for each molecule of product formed. يعني هي مجرد الخطوة الأولى create the radical, and the few radicals can give thousands of products. Termination reaction, chlorine radical with chlorine radical to give chlorine molecule, methyl radical, chlorine radical to give chloromethane, methyl radical with methyl radical to give ethane as a byproduct, methyl radical with methyl radical to give ethane as a byproduct. Alternative mechanism. It seems possible that methane with chlorine radical in propagation step will form CCl bond and H radical, and then the H radical will react with chlorine molecule to give HCl as a second step and chlorine radical. Let's look at the thermodynamic data. Breaking carbon hydrogen in the first step needs 435 kilojoule per mole. Forming carbon Cl bond will give out energy minus 351. Total required for this step is plus 84 kilojoule. Okay? Remember, in the previous mechanism, the first step needed only 4 kilojoule. here needs more, 84 kilojoule. Even in the second step is more exothermic, and the total, of course, should be the same value minus 105. This alternative mechanism seems plausible, but step A is endothermic by 84 kilojoule. The previous mechanism provides a lower energy alternative. When a chlorine atom collides with methane molecule, it will not react to give methyl chloride and hydrogen atom, but will react to give HCl and methyl radical, which needs only 4 kilojoule per mole. Free radical chlorination of hexane gives very poor yields of 1-chloromethane, while cyclohexane can be converted to chlorocyclohexane in good yield. How do you account for these differences؟ ليه الهكسين صعب جدا يديني good amount of 1-chlorohexane بينما الcyclohexane can be converted to chlorocyclohexane in good yield? What ratio of reactant cyclohexane and chlorine would you use for the synthesis of chlorocyclohexane? Cyclohexane has 12 equivalent CH bond. Replacement of any will lead to the same product. However, hexane has 3 different sets of CHs, and monochlorination will produce a mixture of 3 possible isomers. Let's see. In cyclohexane, we have 6 CH2 groups and they are identical via C6x of symmetry. If we have an X here and we rotate this molecule by 60 degrees, we will find that this group CH2 are identical. No change in the molecule. They are really replacing each other with 60 degrees, 60 degrees, 60 degrees. So when you have Cl in the first propagation step, we will form chlorocyclohexane. This is identical to this is chlorocyclohexane. So they are replacing one of these or one of these or one of these or one of these, give chlorocyclohexane. By looking for the hexane, CH2 and CH2 on carbon 3 and 4 are identical. CH2 are, again, they are different from 3 and 4, but they are identical to one another. They are the same. 6 CH3 and CH3 on 1 or 6, they are the same. In other words, if I have to replace one of the carbon 1 by Cl, it is the same this is chlorohexane and this one is chlorohexane. They are identical, the same. Again, if we replace 2 or 5, will be 2-chlorohexane. 3 or 5 will be 3-chlorohexane. hexane. So in cyclohexane, only one compound. In hexane, we can expect three different products. The best way to convert cyclohexane to chlorocyclohexane would require a high ratio of cyclohexane to chlorine. So the chlorine molecule will react with cyclohexane molecules before they ever encounter molecules of chlorocyclohexane. بمعنى ان لما يكون نسبة السايكلوهكسين كتيرة قوي، فان السي ال راديكال دايما هتلاقي جزيئات كتير من السايكلوهكسين فتتفاعل وتدي الكلورو سايكلوهكسين، وبالطريقة دي هيقل نسبة ان السي ال تقابل جزيء تاني من الكلورو سايكلوهكسين ويديني الداي كلورو سايكلوهكسين. دايما هيبقى في نسبة high ratio of the cyclohexane, so Cl radical will really find a lot of molecules of cyclohexane, so it will give monochloro. The bromination of methane proceed through the following steps. Br2 to 2Br radical needs 192 kilojoule delta H to break this Br-Br bond, and the activation energy is 192 kilojoule. CH4 plus Br radical, CH3 radical, HBr, delta H67, and activation energy 75. CH3 radical plus Br2 to give bromomethane and Br radical, that's exothermic 101, and activation energy is 4. The question here is asking us to draw a complete reaction energy diagram of this reaction, label the rate limiting step, draw the structure of each transition state, compute the overall delta H for the bromination. First, draw complete reaction energy diagram. Number 2, label the rate limiting step. Number 3, draw the structure of each transition state. Compute the overall delta H mot enthalpy of the bromination. We will not talk about the initiation, okay, step of the bromination, bromine cleavage. Okay, now we will start with CH4, Br2, that's plus 75, and this is the first transition state. Then intermediate when we form CH3 radical. And then second step, transition state, and then we get to the product. Here, from this to that, this is delta H, and this is the activation energy. Okay? All right? Here, from here to here, this is delta H for this step, and this is delta H for this step. Here, delta E for activation, and this is delta E for activation of this step. The first propagation step leading to the highest energy, see, here needs a lot of energy, high hop. Because this is a high hop, will be the slowest step. This is a slow step, and this is a fast step. Okay, and the low step, we call it rate determining step or rate limiting step. So transition state, to reach transition state 1 will be the rate limiting step, and this is transition state 2. According to Hammond postulate, this is the transition state of Br bond break, and each Br will be carrying partial radical. For the second step, the carbon Cl is going weaker, and HBr is going to be formed, and still here is partial radical, and here is partial radical. In the third one, carbon partial radical with Br to be formed, and Br carrying radical. Remember that this is carbon H reacting with Br radical. Okay, when we get these together, this will be the transition state, and in here this will be reaction of this radical with Br. So when this comes together, okay, now creating partially on this and partially on Br, and this is a transition state number 2. Delta H naught, the sum of delta H naught values of the individual propagation step. The first one, endothermic 67 kilojoule, plus second step is exothermic plus minus 101 kilojoule per mole, and that the reaction will be total exothermic with minus 34 kilojoule per mole. Chlorination of propane. Propane with chlorine in presence of UV light gives 1 chloropropane 40% and 2 chloropropane 60%. Looking for the propane structure, we have CH3 identical via symmetry. So 6, we call them primary hydrogens, and propane also has CH2, so has 2 secondary hydrogens. For the primary hydrogens, it's 40%, but we have the possibility of 6. So per hydrogen, the reactivity will be 6.67%. For the secondary hydrogens, it's 60% divided only by 2 protons, 2 hydrogens. It's 30.0% per hydrogen, which means that the secondary hydrogen is much more faster than the primary hydrogens. We divide 30 by 6.67, 4.5 times reactive than the primary hydrogens. The secondary hydrogen is 4.5 times as reactive as the primary hydrogens. Chlorination of isobutane. Tertiary hydrogen atoms react with chlorine about 5.5 times as fast as primary ones. Predict the product ratio for the chlorination of isobutane. We have 9 primary hydrogens in isobutane, 3, 6, 9, while we have only 1 tertiary hydrogen. 9 primary hydrogens, relative reactivity for each one, let's say 1, and for the tertiary is 5.5. So we have 9 primary hydrogens, so we have 9 relative amount of reactions. For primary tertiary hydrogen, we have only 1 for reactivity of 5.5, so total will be 5 relative amount of reaction. Total amount of reaction will be 9 plus 5.5. Fraction of the primary will be 9 divided by 9 plus 5.5 will be 62%. Fraction of the tertiary will be 5.5 divided by the total. 9 plus 5.5 will be 38%. So getting this compound will be 62, replacing the primary hydrogens, and replacing the tertiary hydrogen will be 38%. Experimentally, tertiary radical is more stable than secondary, more stable than primary, and more stable than methyl. More stable means it's lower in energy, can be formed easily. Various factors responsible for the stability of free radicals are inductive effect. R, we called R group, electron donating group, pushing the electrons away from it, and call it positive inductive effect. Okay, and you can see in the tertiary we have R group are pushing electrons. Okay, so the electron donating inductive effect of the alkyl group, which decreases the electron deficiency of the radical. Of course, this carbon needs 8 electrons, okay, and it has only 7 electrons. Okay, hyper conjugative effect. The odd electron in the alkyl radical is delocalized onto beta hydrogens through hyperconjugation. So this is a beta hydrogen sigma bond. Okay, now which has 2 electrons, of course. This odd electron is delocalized. It's jumping from one of here, and this is going back, and we call this hyperconjugation. It's not bond, but it is localization of electrons. And as you know, the hybridization of this carbon, sp2, where the odd electron occupy the b orbit. Resonance effect. If you have an allyl radical can delocalize, forming here double bond, and the radical will be on that carbon. So odd electrons with odd electron form a bond, and odd electron will be on this carbon. So this is 1 electron, b orbit, 1 electron, and this again 1 electrons, and these p orbital are open and in the same plane, so it's delocalized of electrons, making more stable radical we call it allylic radical. In free radical, where carbon center is in conjugation with double bond, the resonance effect leads to stabilization of these molecules. The stabilization effect of vinyl group in allyl radical and phenyl radical in benzyl radical are very significant and be satisfactorily explained by resonance. The stability of this radical can be easily explained by resonance. Addition reaction to multiple bond as an example of free radical reactions. Alkene react with HBr in presence of peroxide to form anti-Markovnikov product. We will get that in detail later on in alkene. Initiation reaction, the peroxide by heat or light, homolytic fission will give OR radical. OR radical with HBr will form alcohol, ROH, and Br radical. This is initiation step. The propagation step, reaction of alkene isobutane with Br radical will react to form this carbon Br bond, and the radical will be on the tertiary carbon. So it is tertiary radical. If the reaction proceed differently, Br radical this is primary radical. This is primary radical, and the other way for tertiary radical, which is more stable. Of course, tertiary radical is more stable, that this radical will be formed, not the primary one, and this will proceed. So this radical will react with HBr to form carbon hydrogen bond and get out Br radical. And terminations, they include combination of free radicals, okay, to form neutral species and terminate the reaction. Okay. See you in the coming lecture. Bye bye.